The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right. So let me switch over to today's topic. And we'll see some cool demos. So this particular project that Kimo Johnson and Ted Adelson built, they call it Retrographic Sensor, also won the Best Demo Award at CVPR. So we saw this chart last time. We're already selling 2.5 billion sensors in the next year or two per year. And this is the forecast made in 2006-2007. So it might have changed. If you see the integration of cameras in mobile phones, a natural question is, will we even think about a digital still camera as a standalone entity in coming years? And if you think about a wristwatch, I think most of us don't wear a wristwatch anymore. Knowing what time it is not a difficult problem anymore. I don't need to spend a lot of money, or I don't have to kind of tether myself to an additional device to know what time it is. And will we be in a similar situation about imaging? Will we even have a standalone camera for any purpose? So just want to take a couple of minutes to see what opinions you have. According to Nokia, more than 50% of the people who bought N95 got rid of their point-and-shoot camera. And Nokia sells about 1 million phones every day. Okay, they sell 400 million phones a year. So they sell more than 1 million phones every day. So these are staggering numbers. Which is the largest camera company in the world?
Yeah.
Sorry? Nokia, right? It's not a traditional camera company. And the same answer for which is the largest computer company in the world?
Electronics.
Oh. Nokia doesn't build anything of their own, of course. They OEM everything, but still, they're the largest computer company in the world as well. All right. When do you think camera as a standalone device will completely disappear?
It'll never completely disappear.
By completely, I mean less than 0.1% of the population carries it. Let's say something it's like saying when will the film camera will disappear, and I believe it's gone.
Oh, but they're going to be gone in different ways. So digital cameras are going to be gone, and they're going to be everywhere.
Mm-hmm.
And film cameras are gone, and that nobody uses them. So,
what?
I'm sorry, Bjorn is still in the room. So.
Very rare individuals.
Okay, Bjorn, when do you think, you don't want to answer the film camera question, you love it, but when will the digital camera disappear altogether? You don't have anything against digital cameras.
Well, no, I don't have anything against digital cameras, but it depends on your definition of a digital camera. If you're just talking about point-and-shoot cameras,
A standalone, a device that's built specifically for the purpose of taking photos.
Okay, so if you're not going to be a professional photographer, then the average consumer, it's probably just going to disappear maybe in 10 years.
10 years?
5 years.
All right. Anybody thinks it will happen in less than 10 years? Let's say something like that.
Yeah, I think around 5 years.
In 5 years, there will be no standalone consumer digital cameras.
Yeah, I think in just a couple of years, because if you think about it...
In 2 years? Yeah. Wow! let's call all the camera companies.
All the point-and-shoots are already switching over to emphasizing video, and then also SLRs are starting to do video also, because they're not just normal cameras anymore.
Right, but I mean, video camera, still camera is the same thing. I'm just saying, will we have standalone devices that whose only goal is to, yes.
We already have cameras that allow you to upload your Wi-Fi cameras, your cameras that allow you to do some editing on it.
Right.
And there's no reason why this shouldn't be your computer, your actual portable device.
Uh-huh.
Right?
Exactly.
It's basically converting to both sides. Both the camera can do more,
Right.
not just acquisition,
Right.
and your computers can do acquisition too. So
Right. I mean, you're right. I mean, it's going to be some kind of a fusion, but is the camera going to become a phone or the phone is going to become a camera?
it's still going to be one single camera. Oh, so that.
I think in the back.
I'll say a century.
A century?
Yep. The
Wow.
same way that the computers brought us the paperless office and the end of books, and we no longer have stage theater or cinema. We've been predicting that into those for a long time. I don't expect the cameras to go.
Okay. So that's a very interesting comment, right? What's unique about paper or watching movies that may or may not apply to a device?
But in response to what you said, the need to capture images won't disappear, but the fact that there is going to be one device that its sole purpose is to capture images will disappear. And it will be a device that is either a phone and capture images and do your laundry and do everything else.
Yeah, I mean, the way we print books has changed, but we still have books.
Depends on-
Depends what you're doing with the image, though, right? If you're shooting stuff on straight, because they want the image quality. So, I mean, you vacate it now for simulated, but again, there's people that think that that's not good enough. Right?
Yeah, but I mean, here's a hypothetical scenario, right? If I can buy a phone whose image quality is sufficiently good compared to a standalone still camera, that's the question. We are assuming that the image quality is going to be good enough. Let's take somebody new here.
So
Yeah.
I actually really agree with what you said. I think that I actually think it'll never really disappear for a couple of reasons. I think
0.1% of the population. So
all right. So I actually would be curious today how many people carry phone cameras. I'm curious.
1 billion people carry a camera in the pocket.
Okay, but so one reason I think is that there's not only image quality, but there's the ergonomic interaction.
Yes.
Right? And I think the reason why a lot of people carry a DSLR is not just for the image quality, but for having things available in buttons and having human hands are certain sizes and people.
Something that's heavy enough and something you look cool with and so on.
Well, no.
Is it for function or just for fashion?
No, the heaviness does add a function because it stabilizes the image
Okay.
a little bit.
But I mean, I also think that there's something else too. I'm actually unconvinced in general that devices converging is necessarily good. I mean, friends of mine that I tell this to say that I'm an exception because I carry like 2 cell phones and I think I'm carrying 3 cameras right now.
Two cell phones will never converge, right?
They have phones that have 2 SIM cards.
I think there are certain advantages to having actually redundancy in devices and things. So I definitely agree that digital cameras might have Wi-Fi connectivity or other things, but I suspect that a lot of people will carry separate things that are their primary purpose is imaging.
Right.
And a separate thing is also that may also have a camera in it.
And there will always be a film camera in Bjorn's house, even 30 years from now. But we're talking about 0.1%. So let's take a quick vote and move on. So how many people think it's, let's do the reverse. So we'll say 2 years from now, how many of you think will a standalone imaging device will disappear? Kevin? No? All right, we have 1. Okay. Do you want to say very quickly why? Because you...
So far the image quality has been the problem.
Right.
You just don't collect enough light on the sensors that you can fit into a phone, but I think people are finding ways to get around that with software and with optics.
Right. Oh, by the way,
And with the sensor, actually, there's a whole new generation of sensors coming out that allows you to collect much more light.
Mm-hmm. Remember, right now, the total standalone devices for imaging is 10% already. Okay, This is optical mouse, which is not really a camera, we can ignore that. But mobile phone camera, digital still camera, gaming, and so on. So it's already 10%, and we're talking about 0.1%. So let's move on and just let's take a quick poll. So 2 years, we have only Matthias.
Quick question, I guess. Is that even a decent metric? Would it be better to say how many photos are taken? Mm-hmm. Because a lot of people carry cell phone cameras but use them once a year. My mom just uses her cell phone camera. Right. She has one.
The next class will talk about how long will it take before photos disappear. But that's the next conversation. So it's like saying how many people write with their own handwriting. Right? It's the same situation we want to see very soon. But that's for the next class. So 2 years, we have only one. 5 years. Okay, 3 or 4. 10 years. Okay. 15 years. So I guess almost everybody, right? And never. All the power to you.
I'd say one additional comment. We're thinking about this population right here. In most of the world, people cannot go and afford a separate camera. They're going to buy a phone.
That's a good point. That's an excellent point.
You get down to 1% very fast.
Yeah.
It doesn't take that much.
When the remaining 5 billion come
Right.
on board. Yeah, that's a good point, actually.
So,
Yeah.
camera phones.
Right. Yes, Jay?
Yeah, I have a prediction. I think that people that will still have many devices will have Apple device. And we can look at Steve Jobs. You have the iPhone with camera and the iPod Touch with camera.
Right.
You know, they have an iPhone without telephone.
Right.
So it's interesting.
That's just a marketing gimmick, but
Yeah, but it's interesting to think of marketing in this respect. And I think your point is very relevant.
Right.
Some people can afford just one electronic device.
Right.
And the mobile phone makes sense because communication is maybe more important than picture taking.
yeah, I mean, very soon you'll be able to buy a burger with a camera in it. That's your what's the toy called for children? The happy toy.
The Happy Meal?
The Happy Meal, right? And you'll know what you ate and how many calories you had. And it's a whole pot.
It'll trace the burger through your digestive system.
It'll show you how happy you were
And then when you get it out, it's great.
Go ahead.
In this graph, the number of digital cameras is also increasing, followed by the same proportion as the number of mobile phones. So
Exactly. It's mostly mobile phones right now.
yeah, but see, the number of digital cameras is growing part of them.
It's not growing at the same rate, unfortunately. So.
You can't buy a phone without it. It's hard to find a phone without a camera, so it is sort of unfair to look at that.
But that's the whole point of this class. I think we are at a stage where people are saying, "Oh, cameras are cheap enough." By the way, do you have an idea of how cheap a camera is today?
Make or buy.
For a device maker, how much does it cost them to pay for a camera? If they were to attach a camera, how much does it cost them? Okay, $1. Anybody else?
$5.
It's 20 cents.
What?
Okay. So when I said it will come with your burger, I'm not joking. All right. Yeah, of course, it doesn't have power, but it has electronics, it has optics, it has sensor, and it has a compression engine. Right. It's 20 cents. So things are changing very rapidly. And to answer your question on, okay, you cannot buy a device without a camera in it anymore. The problem is, right now we don't have enough services that go on top of those cameras. But imagine if people in this room say, wow, 1 billion people have a camera. Let me try to see if I can build something that really exploits that. Or let me see if I can change the game a little bit, add a little bit extra feature. Maybe add a thermal sensor to it, maybe add UV light to it, whatever it is. Maybe I'll make it into a camera so that, instead of 20 cents, now it costs me 23 cents. It will completely change the game. Right? And the same way we get addicted to our devices and we just can't live without them anymore. Hopefully, cameras will play a similar role. That you will be forced to use the camera. It won't be just an additional feature that never gets used. So.
Did you wrote this or?
About what?
you'll be forced to use it?
I mean, not forced, but you'll be encouraged. How about that? It's like saying, are you being forced to use a credit card?
Yeah, that's what I actually don't like about it.
Yeah.
You are forced to use a credit card.
That's another discussion we're going to have with all our European friends. All right. So, taking notes. As you can see, a lot of our discussion will be not on the slides. So, Sam's taking the notes today. And what you need to do is the slides will be online, so you don't need to capture what's on the slides. You need to capture, all the information that's coming up. For example, JB had a comment on, a new camera, or there are other comments in the back. So you want to capture that in the slides, or anything I mentioned, and also summarize some of the question and answer sessions. And we'll draw some, we'll have some demos, try to take pictures. And I'll do some doodles on the board, take his photo, and so on. And we'll have one student assigned for each class if you're taking for credit. And I encourage you to just use a laptop, because you can probably take notes faster, and you can also look up some information very quickly. And then you can work with me over the weekend, and on Monday we'll post it on Stellar. Right. Is everybody familiar with Stellar website for MIT? How many of you know about the Stellar webpage? Everybody's familiar? Okay. And if you don't have access, like if you're not taking the class for credit, then you may or may not, I think you should be able to access. It's open to anybody in the world. So you can even send it to your friends, and they can look at just the slides. They won't get a lot of the other information, of course. But if you cannot access it, just send me an email, and I can explicitly add you as a guest on the Stellar website. The one benefit of adding you explicitly is that sometimes the announcements go only to the people who are taking the class for credit. It could be about exams or other things. And if you want to participate in that, then you will get those emails as well. Right. Okay, so assignment 1 was about lighting, and that's what we'll be talking about today. Very different ways of capturing light. Does anybody have questions? These are the few things you have to do. You have to have a commented source code, or if you used a GUI-based approach, Photoshop or something, then you need to show me a lot of intermediate results, input and output images. The images should be captured by yourself with your own camera. If you don't have, for the first assignment, maybe you can use a cell phone camera, but see if you can buy, a cheap camera that has a manual mode. You can buy a pretty good camera for less than $150. I recommend the Canon A series. It usually has a manual mode. And another benefit of the Canon series is that we have very good SDK, so you can control the camera from your laptop or from your PC. So I recommend the Canon A series to buy. And then you must create a web page where you will host your solutions for your assignments. And then you should send me a link. And what you update on the Stellar is just a link. You're not going to upload all the images and so on. And then it's perfectly fine to use software you find online. Okay, it's perfectly fine. Don't use your colleagues' software, who are in this class, or software people wrote in this class last year. But you can go online, go to MATLAB repository, and if they have a function for doing XYZ, it's perfectly fine to use it. And then we have a Flickr group page. I believe you got an email from me about the Flickr group page. And all your final results, input and final results will be on the Flickr page, so everybody can see it. And we can write comments about each other's work. Okay? And this will be a good kind of a trial run towards our final project, where we will be doing a lot of commenting on each other's work, giving a lot of feedback and critiques and so on. Okay, so 3 things. Stellar, your own web page, and the Flickr page. Any questions? All right. So, this was simple, and if you have more time, you probably want to do in your assignment something that looks like this, right? Where you can do some beautiful relighting. All right. So some of the assignments, I think we already discussed it, will look like this. Okay, let's start with some interesting way you can think about illumination. So here's a photo from One Kendall Square. This is atomic oils here and so on. And even if you have been to Kendall Square, this photo is somewhat difficult to understand what's going on. You don't even know how many stories this, I guess this is the Draper Labs building has, for example, from this photo, and so on. So imagine if magically you can convert this photo into this photo. From here to here. What are some tricks you can use to do that?
Wait 12 hours?
Somebody. Go ahead.
Photoshop's shadow highlights feature.
Yeah, you can try to stretch the histogram, or you can try to take a really long exposure photo. But this is really, really dark. There's almost nothing there.
Another photo speaks up under light condition.
Exactly. Who was saying that? All right, good. So you just cheat. This was actually taken when I was working at Merle, and this is a view from my office. Actually, it's a much nicer view than the office I have right now.
East Campus is nice.
Sorry.
East Campus is sort of nice.
Yeah, I like the brick texture. It's beautiful. And just take the photo after 12 hours, right? In the morning. Actually, I took a photo at 6 a.m. When there are very few cars on the street, and somehow you want to fuse these two photos into a photo that looks like that. So the static parts are captured from daytime, and all the dynamic parts, like the cars and the Christmas lights and so on, are captured from the nighttime. So you want to make some intelligent decision between which pixel comes from where.
Your color temperature is off.
And the color temperature is off, and you have to make some artistic decisions about that. And you'll always have some issues like this one. I think this guy, I waited all night long, but he was parked all night long, so he just didn't move. So you can see that it's still there. So it's kind of a context-enhanced image, and we're really exploiting natural illumination to capture a new photo. Yeah.
So how was this decision made to what to leave out and what to leave in from the magazine? Was it done by an algorithm or?
Yeah, it has to be done by algorithm, right? So this is what you can do. Just one approach, but maybe in your assignments you'll come up with another approach. In this case, you can just compute the scene contrast. You can just take a 5x5 window and find pixels that have very high variance. And you can create a stencil like this that says, oh, all these pixels look interesting. And now this part here, clearly there's nothing, so I should not take that from the nighttime image. And then I can use the stencil. The black pixels will come from daytime, and the white pixels will come from nighttime. And if you just combine those two using that stencil, you'll get a reasonable image already, but it will look extremely ugly, right? Because the transition from here to here, from nighttime to the daytime, will not look very natural. So what can you do? Any solutions?
Blur the mask.
Blur the mask, you can do that, but then the edges of the building will get very fuzzy. Because it will look like part of the building was in the daytime and part of the building was in the nighttime.
Could you just say how you made the mask again?
This mask?
Yeah.
So, in the simplest case, you can just say, give me the pixels that are bright enough. It's images 0 to 255, anything over 150, mark it as white. That's the simplest thing, but it's not so good. A slightly better way of doing that is you go in a window of say 5x5 pixels, and if all the 25 pixels are the same, then maybe it's not very interesting. Like here, all 25 pixels are the same, or in this region, all 25 pixels are the same. But if there's enough variation between them, if I just take the variance or the standard deviation of those 25 pixels, and it's high enough, then it looks like there's some information in those 25 pixels in a 5x5 window. And you'll mark that center of that 5x5 window as something that's interesting. Yep.
One thing you could do for just around the building is to shrink the components that are not connected or that are too small.
Mm-hmm. Okay. So you can use some kind of a graph cut approach and find some connected components and so on. Back there.
Cheating a little bit, you could have taken a burst of photos and diffed between them to find motion or areas of interest.
Great idea, especially for something that's moving, to find that. But you still have to take some daytime image to fill in the static parts that are dark. But that's right. In fact, that you have to do that for cars, because some cars, the center of this car is too dark, but still important to us. So this is what simple processing would do, but maybe you want to do something smart. So this is just a zoomed-in version of that. And it's trying to capture. All these windows did not have lights on. You see here, but there's one window with light on. I think this is the stairwell of the Biogen building, or Amgen building, and it captures that, right? But then it creates this ugly artifact around that. So you want a very nice transition between the two. So the solution for that is actually called a gradient domain fusion. And that's just a fancier way of saying that instead of worrying about absolute intensities, I'm going to worry about difference between neighboring pixels. So I'm going to take a pixel x plus 1 and pixel x and find the difference between them, and I'm going to blend those ones. Right? So this is what would happen if you just blend the intensities, and this is what would happen if you blend the differences. Now, if you blend the differences, which is just the forward difference, then the image that you will get will be also made up of forward differences. So to go from a forward difference back to the signal, we must do integration. And in 1D, it's very easy, and we'll study that later. But in 2D, it's quite challenging. So it's basically doing a 2D integration from all the forward differences. And putting the two together, again, I'm not going into the detail, we'll study this more. It turns out you can create very aesthetically pleasing fusions or blending between different parts. Yeah?
What if, this is sort of just an example of a night and day image. What if you multiply the images and then normalize?
You could try different things.
Because the dark parts would sort of come through, and the light parts from the day would also come through, and it may actually merge a little bit nicely.
Right. So these are some of the things. It could work in one scenario, but not the other. You're right. And this is exactly what I want you to do in the assignment. The assignment gives you a very simple and very easy problem. But instead of taking pictures under two different flash table lamp conditions, you could take a picture under two time instances, one in the daytime, one in the nighttime, or under two different polarization or anything, and then fuse them. Instead of fusing color channels, you can fuse intensity channels, or you can fuse the forward difference channels, and so on. One great software, it's on the website, I would like you to use for testing. It's called HDR Shop. And it's available for free. It's from a group at USC led by Paul Dababek. And I highly recommend that, because instead of using Photoshop, if you use HDR Shop, again, even if you're doing MATLAB assignments, you can download HDR Shop, and it allows you to do summation of it. You can sum two images, A plus B, A minus. You can subtract the images. You can do forward differences. You can do log intensities and all those things. So it's a really good software for doing arithmetic on images. And all the arithmetic is done in floating point. It's not clamped to 8 bits or 16 bits. So let's say you want to multiply two images, and the intensities are 200 and 200. It's 40,000, the multiplication of the two. And Photoshop, I don't know if it supports floating point numbers, but HDR Shop will support that. And so you multiply, maybe take log of that, and do all kinds of interesting things. So even before sometimes you writing a MATLAB program, you can very quickly do some visual inspection on this. And another trick a lot of people forget about when you're doing assignments or projects that involve the images is don't work on the whole image. Work on a very tiny part of the image. Just take a 100 pixels by 100 pixel crop, not this size, but just a crop. So you have some 2 megapixel image, Don't try to run your code on 2 megapixel image. It might take forever. Just take a very tiny part, some really interesting part. Just crop it and run all your code on that. And when you feel that all your procedures are working, everything is working well, then you can go back to the slightly larger or the whole image. So, when I was working on this project, actually, I was very inspired by this the surrealism era of surrealism, where William McWright and all that came up with Empire of the Lights. I'm sure a lot of you have seen this painting, where he created this very stark, kind of disconcerting positioning. You have bright daylight here, but the bottom part of the image is a nighttime scene. And he played with a lot of this juxtaposing of disconcerting elements. And the question is, can photography create something that is surrealistic? Not always photorealistic, but surrealistic. And when we come to discussion about will photos survive in the future, this is exactly the question that painters ask themselves when cameras invented. There was a lot of interest in creating photorealistic paintings. And when camera came around, they all scratched their head and say, wow, we need to move on and do something else. We cannot create photorealistic paintings anymore. And then we had pointillism and surrealism, and now it's just abstract. We don't even care about representing geometry and reflectance and so on. And the question is, should cameras worry about capturing intensity and shapes and geometry? Right? If I go on Flickr, there are hundreds of images of buildings like this. What's so great about taking yet another photo of yet another building? What I want to create is images that are somehow more expressive and more creative. So that's another debate, whether photos will survive. I personally, by the way, have completely given up on camera. I don't, I barely take photos when I travel and so on. It's just one of those things. I'm well beyond that stage of taking photos. And I rarely get impressed with beautiful photos either. They just look nice, but I never get impressed with that. And hopefully, the remaining 6 billion people will also start challenging the notion of camera as a device that captures, photorealism. I think we have to challenge that notion, just like the painters did, and during Renaissance and during all this era. So, any thoughts, Beyond?
Huh?
Any thoughts?
You've never seen like a photo done by a photographer, like say Richard Avedon or Ansel Adams, that you really like?
It's beautiful, but I'm not impressed.
Okay, here's
can you say louder? She said, what about Ansel Adams and so on? Yeah. I mean, back then when they did it, it was impressive. But now if somebody shows me something as good as Ansel Adams, it's great, but it's not impressive.
Well, so you should look at some of Richard Avedon's like more recent works.
Mm-hmm.
He does some pretty creative things.
Right.
Like there's one he uses a skeleton in some of his photos, and it's like
So the content sometimes is
right.
impressive.
Yeah.
But the art of photography. Comment back there. Somebody had a comment back there? All right.
I have one. I'm not sure you can separate both the technique from the content.
Mm-hmm.
So that's a very good discussion, but I think they kind of come together and create and influence each other as well. So.
Mm-hmm. Definitely need better and better tools and technologies to be able to create something that's really expressive, really beautiful and creative. But there was a time when photographers could impress us based on their techniques. The guy with the biggest camera was called a professional photographer. not the guy with the best eye and somebody who has the patience and aesthetics and all of those things. And hopefully now we have separated the two. Just because the guy has the best gear doesn't mean he's a great photographer anymore. And that's what I mean by. Yes.
His book on that topic as well, going back to like old master techniques called Secret Knowledge by David Hockney. I don't know if anybody else has read that. But, all the different.
Can you just repeat? Is David Hockney?
David Hockney is called Secret Knowledge, and it's going through like all kind of. He worked backwards based on like weird artifacts and their paintings to figure out how they would make weird optical devices to create the original artwork, and like that kind of goes back to the same concept of technique and artist and where those two.
So David Hockney from Ricoh, right?
What's that?
From Ricoh.
What do you mean? What?
The company Ricoh. He's from that.
What? David Hockney?
Yeah.
He's a famous painter.
Oh, sorry. Who's the guy from Ricoh who did all the same analysis? But this is the one where they looked at.
It's an interesting read if anybody's interested on like the history of how these optical techniques played into the role of artists in the discovery. It's kind of controversial.
Yes, exactly. I think we're talking about the same thing. It's very controversial, and he claims that the painters knew about perspective and so on even before the Renaissance and so on.
Yeah, there's a lot of interesting backwards scientific discoveries that he did based off weird artifacts and perspective.
I think it's David Stork.
David Stork, exactly.
From Ricoh.
Exactly.
Yeah.
Is that the same thing we're talking about?
Different, but maybe related.
Okay. I think they do similar things. David Stork writes about optical projections for paintings, and so
it's probably similar.
Yeah. So David Stork and David Hockney. My laptop is rebooting again. That's strange. So I think that's kind of a great challenge we have about how the same way a camera put photorealistic paintings, they made them boring and basically put that breed of painters out of business. What will be the next imaging paradigm that will put today's camera, that will make today's cameras boring, obsolete, and out of business? Because there's only so far you can go with a device that records light and tries to be realistic, with a good signal to noise ratio, converting photons into electrons. That's not what humans do. We don't see with our eyes at all. We just record with our eyes, and we see with our brain. And right now there is very little separation in a imaging device about sensing and seeing. But the whole kind of concept behind computational photography is that these two processes are completely separate. They can be decoupled. You can sense in some crazy way with some crazy mechanism, and then use a lot of computation to create images or create visual experiences that are very different. And if you look at Dan in my group and others have put together this really beautiful digital totem in our area, and it's constantly streaming the most interesting images on Flickr. And if you stand in front of that, you will realize that if anybody's saying that the goal of a camera is to mimic a human eye, and that's what makes it a good camera, that notion will be challenged, because most of those photos which are tagged interesting by thousands of people on Flickr are actually the kind of photos you don't see with your eye. Right? It has some really crazy focus. It has very different color response curves. It has very different zoom and so on. It's basically things people think it's interesting when it's not like what you see with your own naked eye. And that's what the goal. If you take that concept further, right now people are trying to use cameras that are built to mimic the human eye and pushing them to create things that don't mimic the human eye. If you take that further, why not start building imaging platforms that have nothing to do with capturing, a 2D perspective photo. And that's what we'll see very soon. So I'm looking towards an imaging platform that will just create abstract visual art. I don't know what that will be, but go ahead.
I guess it's more a question or topic for discussion. What do you imagine what is the fundamental about photography or about images that makes them lasting, as opposed to the kind of art tied to technology which is batty? Like in the past year or so, we've seen Tiltshift photography be the hip thing to do, and it's
right.
It's entered a land of kitsch.
Right.
Or even HDR, you see a lot of it was neat in the beginning, and now it's kind of feels like it's sort of run its course.
Yes.
And so, but there's still, photography in the traditional sense of capturing what the human eye sees is fundamental in some way, which is separate from the kind of technique, things on top of it. So I guess the question I have is, what is the fundamental of the photographic medium, and in terms of technology, what would be the fundamental technological building blocks, as opposed to separating that from the kitsch?
I agree. I think it's the camera, to me at least, is just a sensor. It's just a transducer. And people say, wow, if the camera is going to change, fundamentally, it's still going to convert electrons into photons, and photons into electrons, and electrons into pixels, and so on, right? I mean, the laws of physics are not going to change anytime soon. How we use it, though, is going to change altogether. And this notion that once you take a picture, that's it. Use the best possible optics and sensors so that you capture an image and that you can see later is changing. So Tiltshift, I'm glad you brought it up, because that's the very next thing I was going to show. Just going before that, I'll come to this. Some other interesting images. A time-lapse mosaic. So again, I started in my office and took these time-lapse pictures. And on the left side is daytime, right time it's nighttime, and all I'm doing is just picking up strips of the images from different time of day. And again, this has these annoying artifacts because it's on some auto exposure, but using a gradient domain technique, you can create a very smooth transition.
But it's still hot car.
Yeah, hot cars.
Yeah, exactly. It still has those problems, right? So, I don't have as much patience, and I'm only doing it sitting in my office. But, it's just a tool that photographers could create, and create images that have a very different notion than what your eye will see if you're there sitting in my office. Of course, hopefully this can be done in Times Square or some really interesting places. And by the way, this one is also catching up now on Flickr. There are a lot of people who are trying to do this. We did this in 2002. Go ahead.
So in lots of examples we saw here, the final result is an image, like a final master in sound, where you do all your equalizing, and there is one sound. And lots of techniques now could be also interactive. You could actually go through the image, go through every point of detail, because what is the final goal is to understand them. There is this idea that there is something complex, you want to do your own interpretation, it could be interactive as well.
Right.
So in all this exercise, the goal is always to create a new kind of static image, or maybe the interactive part could be also interesting.
Yeah, I think you're pointing to a very important fundamental, again, constraint we have put ourselves, that an imaging device should create eventually a 2D photo.
Yeah.
And that's very limiting, extremely limiting. And we will be spending a little bit of time near the end of the semester talking about display technologies. Because unless there is corresponding innovation and research and products and services in display, it doesn't make sense to spend a lot of time on sensors. So yeah, the two have to go hand in hand, and there's some exciting directions there. So the last chapter of our book talks all about these other parallel developments that's going to change how we. So for example, we have 6D display now.
Because even in the simple 2D display, there is this project called Chronos Projector.
Mm-hmm.
Maybe you know there's also in this where you can point any push and you go gradually in time.
Uh-huh.
So it's another way also to explore like this kind of
exactly.
very malleable way, and
exactly.
and by giving the control to the user,
right.
you also empower him,
right.
not just to one final condensed representation, but to go through his own
exactly.
construct immediately.
Exactly. So navigating through photos is a great way, and but at the same time, I love those projects. At the same time, we want to think about something that scales,
yes.
and billions of people can use it.
Yes.
So that's another challenge. So Tiltshift, I'm glad you brought it up. This is the latest fad on Flickr. I think the HDR has kind of it's reaching its bottoming out now. But this is Tiltshift imaging, where this looks like kind of a tabletop toy scene. But it's actually taken from hundreds of meters away. This is in Rajasthan, the city of Jodhpur, the blue city. And that's when you haven't used the Tiltshift lens. So the basic trick is you want to create, instead of keeping the lens and the image plane and the plane of focus parallel to each other, if you tilt the lens with respect to the sensor, then it turns out the plane at which things are in focus, the plane of focus, also tilts. And this is based on the Chamflot principle, and we'll study this in detail when we come back to optics and light fits. But I just wanted to bring this up because it's kind of fun, and you can play with it. All right. So let's talk about some other things. So Illumination, right? You can use it in very interesting ways. Here's a project by, I believe, from Georgia Tech, where they created a anti-paparazzi flash. Okay, and as you can see, the way it works is the paparazzi will take a photo of a celebrity coming out. As soon as the flash goes off, is detected by some electronic device, and it will blast more light so that what the paparazzi will get in the camera is some blown out photo. Okay. How does it work? You can, so let's say this is, let me make sure I understand. Okay. So it turns out a traditional camera, especially a CCD camera, is actually retroreflective. I'll explain that in a minute. So if you take a flash photo of, especially like a cell phone camera, then it appears as a bright spot in the flash photography. So what we're going to do is, this guy here is going to be a camera with ring of LED lights, which is this one here. And right next to it is going to be a projector. So this is mounted in the ceiling, a camera with LED lights and a projector. Now these LED lights are on all the time, and a paparazzi's camera will appear as a bright spot because it's retroreflective. And this projector then, which is right below the mounted camera, will turn on some pixels that are pointed towards this paparazzi. And so basically he'll always see this very bright spotlight being put on him. At the same time, the rest of the scene is going to be dark because only those pixels of the projector are being turned on. And that's why your camera, when it takes a picture, he will just see this really bright source that's glowing out the rest of the scene. Okay. Yes?
What about surveillance cameras and stuff? we don't want to bomb them, right?
Uh-huh. So surveillance cameras are. Surveillance cameras are. What's the question?
I mean, for example, like other, like if for example we want surveillance cameras to just monitor that region,
right.
And then we have this device there that bombs every camera that it finds, then probably we are not capturing any information.
Yeah, exactly. Okay, all right. So the point is that can you try to defeat surveillance cameras? Of course you can. Yeah, there are. We'll learn about a lot of interesting ways you can beat traffic cameras, surveillance cameras, and discuss. But that will all happen at the Buddy Charles at 4:30. What is retroreflective? And we'll look at all of this. Can you guys all see this over here? So if you have a traditional surface like a wall, light comes in and it gets reflected in all direction, and we call it diffuse or magnetic. If you have a mirror, then light comes in and it gets reflected symmetric around the normal. Right? But most surfaces like this surface here, the board here, light comes in and it doesn't reflect in a uniform way and doesn't behave like a mirror. It's somewhere in between. So you get a bright spot, but you also get some other look. So and so on. Is that clear? So diffuse, light comes in, gets diffused in all directions. Mirror goes in one direction, and a shiny surface is somewhere in between these two. Now there are some other surfaces where light comes in and it reflects back in the same direction. And the same surface, the light comes in and reflects back again in the same direction. Okay. And this is retroreflective. Okay. And this is very useful material that you can use in many cases. Anybody knows where this is used? The back of your, the back reflector of the surface of the moon. Very good. Yeah.
On my Vicon system.
Little beads. Oh, that's right. On the beads on Vicon. Yeah.
Are cat's eyes also something similar to?
So cat's eyes work on the same principle as the camera, and we'll see how it works. So human eyes also retroreflect, and we'll see why that works. Okay. So this is principle of retroreflection. How it may work? There are multiple ways you can make it happen. You can just have a so-called a corner cube situation. If I put a corner cube, which is a mirror, then it turns out no matter which direction light comes in, it goes back in the same direction. If it comes from here, let's see, it goes back in the same direction. Okay? So a corner cube is a very useful retroreflector. In fact, if you go to many shops, especially tiny shops, which put mirrors on their walls to make it look like it's much larger through reflections, and you stand at the corner of such if you go to such shops, if you look in the corner, you will see your own mirror image, okay? Which is strange because let's say this is a shop and there's a mirror here and you're standing here. You'll see your own reflection here in this mirror. You also see your own reflection here in this mirror, but you also see your own image here in the corner. And as you move around, this image will move with you. This image will move with you, but this image will always be in the corner. It's retroreflection. I look at a corner, I always see myself. Okay? So I'm surprised we don't have mirror slides in our house, so that I don't have to actually go in front of the mirror. I could be anywhere in the room and I'll still see myself, no matter where I am. So you could build a mirror like that. It's just that you need to do more depth. Yes?
Do you use it also for measuring distance with laser?
Yes.
To go on the street?
Exactly.
They are very expensive makeup measuring this.
Very, very, because the angles are very critical for accurate measuring distances. Yeah. So that's one way of doing it. Yes?
Is red eye reduction also required because of retroreflection?
Very good point, very good point. So red eye reduction is like cat's eyes. You see, and the color red is because of the chemicals in our viscous humor that reflects most of red color.
You can have liquid also, gel, that could do bubbles that can.
Exactly. So bubbles are another way of doing it. So one is corner cube. The other way is. Oh, by the way, another interesting property of this one is how people will say in the mirror you get confused if you move your left hand, your right hand moves, and you move the right hand moves. The corner cube that doesn't happen. If you move this hand, the other hand moves. If you move this hand, so it's your image is not flipped with left and right. It's like this. Try out. Is there a shower on here? Did you ever like this? You use it a lot in teaching methods. Alright, so other one is bubbles. If I just take a shiny, just a glass bead, light comes in, it reflects, because of just refraction. And then it reflects again because of total internal reflection. Because the refractive index here is plus pretty much there. And then it goes back out, and then it gets reflected back. Okay. So that's how a glass bead-based retroreflector will work. And then of course you'll have a bunch of these. So you get light back from all of this. That's exactly how a rainbow works. When you see a rainbow after it has just rained, this is how rainbow works. If you have to see a rainbow with maximum kind of most vivid colors, what condition do you have to satisfy? With respect to the sun and with respect to the highly high humidity air. What's the geometric condition you have to satisfy? You have to be straight line. Yeah. So this is the sky. The sun is just setting. You are here, and you're going to see it exactly in the opposite direction here. So the rainbow is going to appear here. So very common. You go to some place with a waterfall, and you want to see the rainbow. It's very challenging. You can see it sometimes, you don't see it sometimes. All you have to make sure is that the sun, so usually if you're high enough, you can see the rainbow. Because as you can imagine, if the sun is pretty high in the sky, you'll never see a rainbow. Because it's occluded by the surface of the earth. But when the sun is low enough, you will see the rainbow. On the other hand, if you're on a mountain, right, then even in the daytime, you could see the rainbow. If the air is here. Because all these water particles are allowing you to see the retroreflection. And we'll come into why you see the rainbow. Because the refractive index for different colors is different. So that's why we see different bands of these colors. So a lot of fascinating properties of retroreflection. So in case of why does a human eye have red eye, or a cat has bright spots, it's the same reason. So all you want is a property where light goes in, comes back in the same direction. So if you have now a again, please. I don't know if light is here. So now if you have let's say a camera for now, and human eye works almost similar way. And there's a bright spot, bright light, and I'm going to stand right next to it. Light goes in, and this gets focused at some point on the lens. As you can imagine, if your sensor actually has a shiny film in front of it, if you look at a sensor, you'll realize it's pretty shiny, right? It has partial mirror-like properties. Light goes in and it reflects. And no matter where the light comes out from, because of the duality of the light, it will go back to the same spot. Okay? Now, of course, if it is out of focus, you will not see it, because it will go somewhere else. But if the point was in sharp focus on the sensor, it will reflect back and come back in the same way. And so this is the same reason why for human eye, again, you have the same situation. Light goes in, it reflects and comes back in the same direction. So the reason why they tell you, what's a good strategy for removing a red eye? I mean, what should you do? Flash up, or if you have a cheap camera, what do? Don't want to look at the camera, right? Because you're not looking at the camera, the image that's being formed is forming somewhere else, image of the light, because you're looking somewhere else. And so it will not reflect back to the camera.
So the anti-paparazzi system will also blind everybody that walks in the street.
If it was
if you look at it,
if the ceiling mounted light was omnidirectional, then yes, it will blind everybody. But because it's a projector and it's going to shine light only at the guy where it finds a retroreflective spot. It finds only that part of the ceiling. Yes. Or his camera.
We don't want to mess it up. I think the point JD was bringing up is that human eyes are also retroreflective, so if you look at that spot, it'll detect you and flash you.
Okay, is that what you're saying?
Yes.
Yeah.
Because
So
like a camera,
it's true. So the system is not very robust. So please don't go there with your Markham gloves.
with sunglasses.
So also that red eye issues are very ethnically dependent. Usually Caucasians have more problems with Asians. Asians don't have as much problem with red eyes. And that's just because, the pigment and so on. But you're right that if the system works really well, it will also blind probably someone else.
So if you have a mask, something to protect your lens, then this ceiling mounted thing will not be able to see through the...
Oh yeah, that's the next project we should be working on. Now, how to beat the anti-paparazzi system.
Don't use flash. Use a camera with a high ISO. Just get around.
Yeah, I mean, there are a lot of ways to get around it, always. If you want, we'll have a very nice discussion on how to change your license plate so that the high-speed, whatever, the speeding cameras will never be able to see it. You have to buy me a beer, though.
Okay.
All right?
Yeah.
You're up for it?
Yeah.
You're over 18, right?
Yeah, 21.
I didn't ask you that. All right. Good. So, before we take a short break and go into the Illumination more discussion, I just want to give you the kind of final projects you could be working on. Remember, we are really here to do something that's cool as well as novel. Okay? So, many times I'm going to bring up a list of the kind of projects that are not cool. Right? And again, no offense to somebody who might be working in a similar field, but just let's be honest. Let's do something nice. So here are some suggestions for types of final projects you could be doing. You have, beautiful user interaction devices. They're always fun. Instead of using a 2D sensor camera, maybe use the line scan camera, like the photo finish camera. Or which can be, by the way, created from a flatbed scanner. You can buy a flatbed scanner for under $100, and it's actually a multi-thousand frame rate camera. Okay, you can just hold it in one place, and if you walk in front of it, you'll basically create a photo finish camera. You have. There are a lot of issues, but we'll help you on that. This, like Dino was saying, it's not something you can just buy and just plug it in. You have to get your hands dirty in all of this. Or just use photo detectors, single pixel cameras. You can do a lot of interesting things with it. You can include some interesting illumination. Capture the invisible is always my fascination on how can we capture something that cannot be seen with a naked eye. So maybe build some tomography machine that can see inside the body. Some structure like 3D scanning or fluorescence, and we'll see that experiment here just in a minute. And this is a question you were asking earlier. Are there cameras in other domain, electromagnetic or audio or resistive? So how about an audio camera or a magnetic camera or a capacitive camera? It's very, we won't be discussing it a lot in the class, but I think it's a great way to do a final project. thermal IR camera, and we can help you. Maybe a thermal IR camera that detects emotions. Multispectral camera, cameras that can distinguish between two very similar colored objects. People are always interested in distinguishing camel from sand. So, can you create some mechanism so that two very similar looking objects can be completely distinguished? There's a lot of market in the golf business where people want to spot their golf ball on a green background. So you just put this. Do you know what they do? Yeah, they sell it for hundreds of dollars. All you need is a blue filter. If you put a blue filter, all the grass, which is green, looks black. But your ball, which is not green, stands out. Right? So you have a black background and anything that's not green will stand out. You can. There are lots of other businesses like something like that. Illumination, Schlieren photography, I think we saw earlier. A lot of fun. All kinds of strobing. Non-imaging elements such as gyros, GPS, interaction between two cameras. Maybe there is some lighting communication or Wi-Fi communication between them. Optics is always a lot of fun. Camera arrays, light fields, coded aperture. Maybe try to mimic a vision of one of the animals, or study. Bring some worms or bring some cats. And cats have, by the way, really beautiful mechanisms of how they work. And we'll have a whole lecture on animal eyes. I think 7th or 8th lecture. So we'll study that. And time-lapse photos are so much. There's so much information in time-lapse photos. I mean, I wish I could go on Google Earth or Google Street View and it would show me time-lapse. It can't be that difficult. They have to scale their database only by a factor of 24, which is not that much more, I think. But it would be nice to see the same place in the daytime and nighttime, and what kind of traffic it has and what kind of people it has. And right now, it's very static about its appearance. Somebody had a very nice idea for time-lapse photos for Google Street Map, which is sometimes you don't need a video of what's going on there, but the world, at least man-made world, usually only have a few discrete steps. If there's a traffic light, it just switches between 3 different colors. If there's a bridge on river, that drawbridge, it's either in this position or this position. There are a lot of these discrete things that happen in man-made world. So it'll be nice if in Google Street you can see all those discrete steps, discrete situations by just clicking on it. You can create this direct global separation. I think we saw that earlier. Create new types of cameras that are very thin. These are all suggestions for final projects. Mimic animal eye. Play with photonic crystals. They are very easy to make now. Photonic crystals are basically, in simple words, these are ordered arrays of materials that have different refractive index. In the simplest case, it could be just glass and air. Okay, so if you just create, micron scale holes in glass, it behaves in very interesting ways. So maybe somebody will play with that. Student photography and
so Ramesh?
Yeah.
You say it's very simple. How do you do that?
By simple, it's the idea is fairly simple. Actually, when photonic crystals were invented in Bell Labs, they literally took CNC machines in metal and they just punched holes.
Do you have access to that?
We have a microelectronics laboratory. I think Quinn knows about it. Okay. We can. I think they have some charge, but I can easily take care of the funding for that. I think you pay like a fixed 1 hour rental for it.
Okay.
But if it's a research project, maybe we can even get around that. So, in fact, you can buy now nanomaterials and photonic crystals just online. You can get like 2 micron beads and 6 micron beads. 2 nanometer beads and 6 nanometer beads online. Very toxic, a little bit dangerous, but there are certain varieties that you can just use. So it's a lot of fun to play with that. And here are some sample projects from last year's class. Schlieren photography, again, this was the only undergrad in the class, and he won the best project award from Nokia. Jesse from mechanical engineering did a camera array for particle image velocimetry, and now it has become his PhD thesis, and he's applying for hundreds of thousands of dollars in grant. Bidirectional screen was a project by Matt Hirsch. Again, it has become his master's thesis, SIGGRAPH paper, and so on. Ahmad Kirmani in my group, he just looked at the theory. He didn't have time to build anything at that time. Or looking around a corner, which is again a paper this year. Somebody's building a tomography machine, and so on. Lots of cool things. As you can imagine, last year the emphasis was it was a little bit more hardware intensive because the people who are taking the classes were interested in that. But this year we have a more diverse crowd here. So I'm expecting projects in just art of photography, beautiful synthesis of images, HCS, real-time HCI systems, maybe some different types of scientific imaging, maybe a new microscope, anything of that variety. And we'll spend a lot of time together. We have 4 or 5 mentors assigned who are working with you on the final projects. All right. So let's take a short break, and in the short break we're going to show you some cool fluorescent demos here, and then we'll start back in about 10 minutes to talk about other types of illumination. So here's a big question for photography. 1930s, we had big cameras. The guy had to get under the cloth to take a picture.
It's actually a press camera. It's pretty small, and people.
This is more recent, but I'm guessing you have cameras that are bigger than this, right?
Yeah.
Okay. And there's nothing wrong in having large cameras with you. And that has shrunk down to something this and this and 20 cents with all the electronics and processing and so on. But when you think about lighting, not much has changed. It has definitely not reduced in size. It definitely has not reduced in cost or convenience, and so on. And in a way, what really distinguishes consumer photography from professional photography is not the camera anymore, but the lighting. So this is kind of a challenge for our community, who we like to think about making everything programmable and easy to use. The same revolution, will that happen for illumination? Okay. So we're going to explore that a little bit in today's class, and come back and talk some more in the next class. So when we thought about cameras, we tried to make it very smart, with the lenses and different sensors and new processing, but the light source is still a flash. Maybe it has fancy umbrellas and so on, but it's mostly a flash. So what we want to do is replace that into a more programmable illumination in a very high dimensional way. It's geometry, we'll call it 4D illumination field, in time and color. Right? So some of the earliest examples, and this whole field is called computational illumination. We're going to use computing even in the lighting. And maybe the pioneer was Doc Edgerton, right here. Very famous examples of bullets going through an apple. And Santiago was saying you have this one, or
the 3 balloons.
3 balloons, yeah. So Edgerton has this beautiful pictures. Are they in your dorm as well?
The same one.
The same one? Yeah, great. So beautiful pictures, but they were not captured with smart cameras. They were captured with smart lighting. Okay. You have an ordinary camera where the shutter is open for certain duration, but then you have a flash that freezes that motion, which Edgerton called a stroboscope. And in this particular case, you have a sequential strobe that captures this whole circle. Right? Nothing smart about the camera. Really smart strobed lighting. And of course, Dr. Edgerton came up with chemical processes to create very short duration light sources. But now we have LEDs and solid state devices. We can control light down to few picoseconds or nanoseconds. All this can be done very easily in your house. So again, this is what distinguishes consumers from professionals. And we'll look at this step by step. And this will be more technical discussion about what parameters of light we can change. Okay. So let's think about what are the things we can change about light. One is clearly the brightness. What are some other things we can change? Color.
The collimation.
The cone. Polarization.
Coherence length.
Coherence length, a little bit more exotic, yes.
The direction.
The direction, yes. Maybe it's not even a single cone, but just like a projector, different directions have a different intensity. Time, so strobing or duration or synchronization with the captured image.
Relative phase.
Relative phase, of course.
So lenses on your lighting instruments.
Put lenses, exactly. Don't think of your flash as just a light source, but put fancy optics or masks in front of them to control, again, direction and so on.
You can put light inside the object.
You can change the environment, not just illuminate the environment, but change the environment by putting some interesting lighting inside there. So, this is by the way, another great way to come up with new ideas. You say, this picture really bothers me, right? What can I do? And if you want to do research in this area, you ask this question to yourself. What are all the ways I can control the lighting parameters? And I'm going to go through one by one and see how I can attack them. Okay? And we'll see examples of exactly how that has happened over the last several years. So, the simplest one is I can have light or no light. The simplest parameter. Next parameter is duration, how long it's on, or its brightness, and so on. Its position, its color, using it as a projector, modulation in angle, modulation in space, modulation in time, and sometimes just natural light, just time lapse, which we saw. Right? So we'll just look at a few projects to get us motivated. And we saw this one last time, a multi-flash camera, where we're really trying to solve a new problem. If I want to tell you what's inside my car, I can just take a photo and send it to you. But when car companies want to do the same thing, they hire artists. So the question is, why do we hire artists to draw something that can be photographed? Yes?
You might know what's more important or less important.
The semantics is very important, yes? Yes?
What's a thing and not a reflection? So like edges.
Yeah, reflections are annoying and they don't really add any information, and edges are more important, right?
In that picture also the essential elements are highlighted.
Exactly. The hand is brighter than the rest of the car. Is that what you mean? Yeah. Yeah.
Some unnecessary wires or gadgets.
yeah, all these things is just clutter, right? I mean, it's not critical to explaining what's in the car. It just looks more beautiful. So, unnecessary shadows, clutters, too many colors, as opposed to highlighting the shape edges, marking what's moving, and using very simple, basic colors. Yes.
Is this what we call diminished reality compared to augmented reality?
There are some other names for it.
Non-photorealistic.
Non-photorealistic. So, imagine if you can just build a camera that gives you an image on the right as opposed to the left. We are not trying to put the artists out of business, but we are trying to create tools so that they don't end up time rotoscoping and drawing the lines. They get all the line maps very quickly, and then beyond that, the creative process starts. Okay, so get rid of this tedious task of finding the edges and marking and so on, like all the magic scissors and so on. So, of course, the first solution would be just take the photo and try to find intensity edges. Turns out it doesn't work very well, right? And this is a problem you face in HCI all the time, right? You have some gestures with your hand, which might have some challenging background or lighting. Then, a typical method is to maybe do some kind of edge detection, color detection, and you just hope that, the lighting is just right when you're showing the demo, and you have managed to control the background just enough so that, everything works out. Or you can be smart about it and distinguish between reflectance edges, which are edges between different materials, and distinguish them from depth edges, which are real geometric edges. Okay, so these are all intensity edges, and these are all just geometry edges. So imagine if I could take a photo of this and get this out. Clearly, it will be much easier for me to write an interactive system that's based on that.
But this is really like a computer vision question. Actually, like the example with the car, that's like maybe like questional meaning because a human being knows what to abstract and
yes.
what not, and they don't really emphasize.
It's multiple goals. So one goal is diminished reality, trademarked by. Sorry?
It was already defined by the internet.
Okay, all right. So, Ankit, who's a scientist in our group, has a very interesting way of putting this. He says, photography is, is well known as photography is the art of exclusion. De-emphasizing things that the photographer makes a decision on what to de-emphasize, either by using focus or by cropping it, and so on, so that the photographer can convey to the viewer what's most important. But what we're doing computationally now is adding another level of exclusion. In this case, we're excluding the intensity edges and just keeping depth edges and all these other things. So computationally, we should be able to extend the concept of exclusion. So one could be for non-photorealistic rendering, for creating cartoons. One could be for HCI, and there are lots of other things. Right now this is being used in Mitsubishi products for some really bizarre things. So we saw the idea last time. You get the slivers of shadows, and by analyzing the shadows, you can compute the depth discontinuities. And some people like to call it silhouettes. Some people like to call it occluding contours or shape boundaries, but they're not so precise, and depth discontinuities is what we're really talking about. So when I take a photo, then the depth of this pixel and depth of the pixel on the other side of this screen has a C0 discontinuity, and that's really what we're talking about. As opposed to silhouette, where it's usually about just the external part, but if I put my hand over here, this is still a depth discontinuity from my hand to my body. So I would like to capture that. And shape boundaries is also not very precise. So depth discontinuity is really what we're talking about. And imagine if this is in the Sony iToy or the Microsoft Natal, then if you have a depth camera, if I put my hand really close to my body, it cannot distinguish the depth with respect to the camera of my body versus my hand. But with this camera, I can still continue to detect that there is a shadow that's created from that.
How about that laser?
Sorry?
The laser projector camera?
Yeah, so actually the Microsoft Natal uses this prime sense sensor, which is not time of flight, but based on triangulation. But anything that senses depth, as opposed to depth discontinuity, will have the same problem. Because as you get closer and closer, you'll not be able to detect it.
We were testing it with a piece of paper. It seemed to be pretty good.
It was very good. Yeah, it was very good. Yeah. So if it's a really good depth sensing camera, then you're all set. But it has low resolution, and it's a more complex device. Okay? So again, shadows to the right, shadows to the left, and so on. But when you look at the shadows, they are not just 1 pixel wide, right? They could be, depending on the depth difference, they could be very wide or very narrow. So you want to create an output that's exactly 1 pixel wide. So how does this work? So before we go there, I guess these are intensity edges, these are depth edges, and you can just put that together to create a cartoon in real time. In fact, we demonstrated this. So here, this is another example, my old 93 Honda Civic. And this is what you will get if you use the intensity edge detector. This is what you get from the 4 flashes. You can even see the Honda sign here. That's barely visible here. That's because the Honda sign is has a relief. It's a height field. It's a geometry rather than texture. And all this scratch marks and rusting is just texture. It does not contribute to the geometry. And if you try to locate the spark plugs or the dipstick, it's barely visible here. But again, here you can see it very clearly. Right? So the shapes are what we're looking for. And these are the 4 images, input images, just raw images. You can see to the naked eye, they look identical to a naive observer. But if you look at the shadows, here the shadows are to the right of these pipes. Here the shadows are to the left of these pipes. Here the shadows are at the top. And here the shadows are at the bottom. And by analyzing the shadows, you can find the depth edges. Yeah?
In practice, how, obviously the farther you took this from 20 feet away,
right.
It's not as effective because your flashes are pretty close to the way.
Exactly. So we'll talk a little bit about what parameters you have to choose to get an optimal performance. And there's definitely a sweet spot where it works in a system. Some more examples here. And I'm just going to describe you very quickly the geometric parameters that make it happen. But we were showing this live at SIGGRAPH. So you can stand in front of this camera where every 4th frame had a different flashlight going off. We put an LED and you can stand in front of it, and it's cartoon. And I'm a big fan of the AHA video from the 1980s. Take on me. You remember that?
Yeah.
Wow. I thought I was too old to appreciate that. But so in the AHA video, there's this very beautiful effect where on one side of the glass pane, the world is cartoon, and the other side it's real. And so when we were showing this, it goes on for 4 days. After the end of the first day, people started saying, "Oh, this reminds us of the AHA video, the Take On Me video." And I said, "Yeah, that's really true." So we got really sick of those comments, and on our demo, instead of calling it, we had some really boring technical name. We said, "This is the AHA demo, Take On Me demo," and we had big letters on a huge screen. And then on the second day, the curator of the show came to me and she introduced me to this guy, and she said, "This is I forget his name, David Patterson. This is David Patterson. Do you know him?" I said, "I don't know him." He said, "He was the music video director of AHA." And so I said, "Wow, that's great. We're really inspired by your video." He looks up on the screen, and our demo was inside a closed booth, and we're showing the live output of that on the big screen. And he said, "What are you showing there?" I said, "This is live. You can go inside, and this is being computed in real time." And he said, "That's impossible, because when we were doing it in mid-80s, every frame took them a whole day to rotoscope and edge and so on." And so we're very excited. Patterson is here, so he comes inside. He acts very cool. He looks at it. He looks at the images, and we get very excited. We take pictures with him. He leaves, but after half an hour, he brings his son with him, and he started explaining to him. His son is like 2-3 years old. He said, "Wow, remember in 1980s I worked on this video. These guys are doing it in real time now." And we said, "Well, I'm pretty happy. You brought your son. You must be excited." After a couple of hours, he brings his wife, and it just goes on all day long. He just keeps bringing people to show them how this works. So that was the high point of that figure. So how does it work, right? So you have a camera and you have your flashlight, which is shown as P here, and then because of the parallax between the lens and the light source, you're going to cast a shadow of this object. If the flash is to the left, the shadow is going to be cast on the right. And if you just trace the ray from the light source to the object, to the shadow, it's going to be projected in the image as this particular vector. Okay. Now, what's interesting is that I need at least, it turns out we need at least 3 light sources. You don't have to use 4, but you need at least 3 light sources. And let's say you have 3 light sources, P1, P2, P3, and the image of the light source is denoted by E. So the shadow, it turns out, lies along so-called epipolar ray. Those of you who are familiar with epipolar geometry. And as long as we make sure that for any given silhouette, any given depth edge, there's at least one light that's on one side of that edge, and there's at least one light that's on the other side of that edge. We can guarantee that at least in one image, you will see a shadow, and at least in one image you will not see a shadow. Okay? And by being able to compare, so out of 4 in our case, at least one of them will have shadow, and at least one of them will not have shadow. So by guaranteeing that, we can analyze the 4 images and compute how that works. So here's a very simple example. Flash is to the left, so the shadow is on the right. Here the flash is on the right, so the shadow is on the left. And all you do is take these 2 images, find the max operator. Take the max at every pixel. Okay? And this is what you can do with HDR shop. I don't know if you can do it with Photoshop. Can you just take 2 images in Photoshop and find the max of the 2? At every pixel, I want to compare the 2 pixels, and I want to take the maximum of the 2. You can do that?
I've noticed that there are filters that you can do that with one layer and the layer behind it and see interpolation between them. I don't know if it's exactly that effect, but
yeah,
there's a list of like 20 filters.
Exactly. But nobody cares about doing nice, simple mathematical operations. So HDR shop is great for these things. All these things you can do it in HDR shop in 15 seconds, literally.
Another tool, I don't know if anybody knows it or uses it, but if you're doing a lot of image processing, ImageJ is really nice.
ImageJ?
ImageJ.
Okay.
It's Java-based and all open source, so if you want to take a look at the code, it's all there.
Excellent.
And it also, you can script all of these functions with the live images using JavaScript.
Excellent.
Which is really useful.
Just send a link to the class or to Sam, so it will go in the notes. ImageJ. And there's also OpenCV and all these things, so I'm sure you'll use them. In MATLAB, again, it's one-line command, max A, comma B. Right? A vector, B vector. But basically one-line code to take a max of 2 images. In Photoshop, maybe 30 minutes. So all you do is take the max of the 2 and take the ratio of this image by the max image, which I call normalized. We're going to divide that. And if you divide, all the texture goes away and only the shadows are left. Wherever there was no shadow, you'll get a value of 1. The ratio is 1. Wherever there's a shadow, you'll get a value that's close to 0. Not always 0 because there's some other lighting. And now, all you have to do is, if you take one scan line here, this is how you plot it, and you can see the shadows very clearly. And same here. In the left image, you scan from left to right, and wherever you see a jump from lit area to an unlit area, has to be a depth edge. In the right image, you scan from right to left, and wherever again you see from lit area to an unlit area, that's the depth edge. So in every one of those 4 images, you'll be able to find depth edges from different orientations. And then we can take a union of all these 4 images, and that gives you a full depth edge. Right? So in this case, for example, all these internal edges are completely ignored, and all you see is silhouettes. And in MATLAB, that's all there is. 15 lines of code and no parameters. No tuning required. Okay? There's no constant that's used anywhere. So it's extremely easy to use. You can implement this. You can use it. I'll give it as an option for one of the class assignments. So you have a choice to use this in real time. Any questions on this one? Yes.
So you said outline, the boundary is only 1 pixel wide, but if you actually provide more than 1 pixel, depending on how thick the shadow is, can we get more depth information?
That's a very good point. So depending on how far things are, so here, for example, the shadow is wider than here, right? And that's because the depth difference is larger or small. So you're very right that the thickness of the shadow actually tells you a little bit about the depth difference. Not the depth itself, but the depth difference.
So you get more 3D information.
So you could get a little bit of 3D information as well. Yeah, that'll be a nice project.
Do you know if there are commercial systems that use this to do a 3D capture?
Mm-hmm.
So are there systems that use this, like we have a machine in the shop
Right.
that takes 3D picture? But
Yes.
you know that, or it's about
They just use a laser scanner usually.
Yeah.
Yeah, unfortunately.
So it could be a cheap way to do it.
You can just capture all the silhouettes. But remember, we are not capturing depth. We're only capturing depth edges.
Yes.
It's like saying I'm not capturing intensities, I'm just capturing intensity edges.
But if you use stereo theory, you compare
So this work has really taken off. There have been lots of papers that are based on this particular technique. And so people have tried to do stereo. Some people have tried to do some, I mean, it's still open. It's very new, right? It's only 3-4 years old. And people have tried to do different colored lights. So there's a lot you can do. So the question back there?
Could you actually capture that, but at least the sort of difference between different edges, just by looking at the size of the strap?
If you can process the shadow width, but remember, it's not going to be as robust because, if you look at this plot, you have to estimate how wide this region is. That's shadow. So if you can do that fast enough, then yes, you could do that. So it's not, in certain conditions, maybe it's possible. Like for skin, it's very easy because the shadow color is not going to interfere. If something was black in the scene, then that could be detected as a shadow. But in this method, even if the object is black, it doesn't matter. You'll still get very nice edges. But if you try to estimate the shadow width, then you have a little bit of issues.
Again, all of this technique assumes that you have one plan, one image. If you could have like multi-focal or I mean, you can then mix all the.
Hey, now you're thinking like a researcher. Now we thought about all the ways you can change the lighting parameters. Now you're saying, in addition to that, can you change camera parameters and do something more? That's the kind of thinking I want you to have in this class. Always take an idea, X, and think about how you can do the next from X. By the way, I posted some slides on how to come up with new ideas on the Stellar webpage. If you're inspired by an idea X, how do you come up with the next idea? And then there's a very systematic process how you can come up with great ideas. And also, the same slides tell you if you come up with a great idea, whether to decide whether to pursue it or not. So I'm curious about your comments. It's just work in progress. I have been putting it together over the last several months. Okay. So again, that allows you to do this in real time. What are some other things people are doing? You take a flash photo. The person is very brightly lit. The background is not so well lit. You take a no flash photo. Okay. What has changed in the two? She didn't blink, remember, despite the red flash. But anyway, that's a different point. What information can you recover from this?
You can separate foreground from background.
You can separate foreground from background because the foreground is well lit, but the background doesn't change. So if I just take the ratio of the two images, it will look something like this. Okay, if I do 1 minus the ratio. So the background hasn't changed. And the foreground has changed dramatically. Right? So this particular paper called flash matting, as simple as that was the idea for Cinegraph paper in 2006. They went a little bit beyond that, and they said if you just take pure ratios, then you cannot get the strands of the hair and so on. So they used some gradient domain techniques, some graph cut techniques to solve this matting equation of what's foreground and what's background, and they can also detect this very subpixel features, strands of hair. And then, of course, you can take that and replace the background. So it works mostly well. It does pretty well here. There's some small artifacts, but it looks beautiful. So just by changing the light, also, just presence and absence of light, you can create some really interesting photography or for interactions.
Is the same technique with like a flashing IR to do live video?
That's a great idea. So you could do alternate frames,
right.
And it won't be disturbing for the user, and you can just distinguish foreground from background. So very simple examples will progressively look at more and more complex ideas here. But let's stop here for today, and we'll talk about all these other cool things next time.